Okay, so this is the Dijkstra question. What's the do in this question there? Since in my previous video we have to explain this, we have to return the shortest path from the source to the corresponding nodes there, and we have to return that distance vector there. Okay, so now there's the previous case in which, but there is a one slightly the electrical change there. In my previous case, what are the case there, or what are the given condition there? All of the edges are of the weighted with a unit 1 there. Okay, so this is the case that I'm using there. But now in this question, the graph remaining the undirected, but now it become the weighted, and all of the edges weight are different, they are not same. See, in my previous case I using the unit edges, so I don't preferring the edges magnitude should be the 1 or 2. It doesn't matter. What the things matter is whether all of the edges weight is same or not. Okay, so in this case we have to take our different edges there, different weights there. Let's say there is a 3 there, let's say there is a 4 there, let's say there is a 2, and let's say there is a 1. Similarly there is a 2, and at last there is a 2 there. Okay, and now I can erase this part there, since we are erasing this part there. Okay, don't have to. Okay, so now this is the case. Initially we know very well, you can see my previous video where I have to explain how I do this by simple my BFS or a optimized part, but now I have to use my Dijkstra part there. Okay, so now what's the thing here? See, simply initialize our the distance with a minus infinite, we can say plus infinity there, so that to track distance minimum. Okay, similarly we have to use the Q there. In my previous video we are using the all of the unit wedges are with the unit 1, so that's why we have to simply add this one there. Okay, means see, this is my whether in my past I have to reach that point or whether I have to reach that node, so this is nothing but that distance. Now if my current distance, so this is nothing but this is whole is my current distance. If it current distance is comparatively good that my previous case, so only in that case we have to update this, otherwise we have to skip that part. Okay, or it means what how to do update this, simply update this. And now since I'm talking about that particular node there, so I have to push this in our queue there. Okay, now in this case since there is a distance is varying, so in my unlike the previous case, there is a we have to simply use our queue of int. Now we have here we have to take the pair of int comma int. Okay, so now here it is nothing but the int comma int, and what is the meaning it's, so it is nothing but the first initially I have to use the distance, and after it we have to use the node there. Okay, so now there is one tricky thing there. First initially I am using the queue data structure. Now I have to after it I have to explain you why it's fail, or we don't have to say the fail, it may be the run, but it should not be the preferable. So we have to change our the data structure, what should be the new data structure, and how to deal with that part here. Okay, so we will see that in my previous in further cases there. Okay, so see, let's some kind of dry run for this part. Since we have to start with our source node, so simply update our source node, and see these are all of the infinite there. Let's say I have to use there, this is nothing but the INF there. Similarly this is of INF, similarly this is of INF. Okay, so it means initially all are taking the infinite distance there to reach from the 0 to there these nodes there, and since we are standing at this node, so that's why the distance is 0 there. Simply updating this is 0, 0. Okay, so we can update this 0, 0. Why it is, this is nothing but the distance to reach there, this is nothing but that node, particular node there. Okay, now we can say, okay, now see I am reaching to this node there, and what are the distance, take it as a 0. Now after it can go to its neighbor. So what are its neighbor? So its neighbor is 1 or 2. Okay, so I'm reaching to the 1 or 2, and what are the distances, it takes from the 0 to 1, so it takes the 0 to 1, it takes the 3 distance. Okay, so I'm writing this as a 3 here. Similarly it takes the 0 to 2 as a 1 distance, so it takes as 1. Okay, now initially it takes 0, it after it it has to take 3, so total distance it becomes as a 3 there. Okay, I can write this using this. So let's say if I'm using this, so it is nothing but the d is equal to 3. Similarly for that case also it becomes the d is equal to 1, 0 plus 1. Okay, this is nothing but the distance required to reach to that node, and after it we have to add what are is weight of its, or we can say the what are its edge weight. Okay, so total it become the total distance to reach to this 2. Okay, so this is nothing but the 1. Now we can see, now since there is a by this method it has to take the distance as 3. Now compare with our distance vector there. Initially or in my previous past it takes infinite, now it takes 1, it takes 3. So what are it? So can we optimize this part? So yeah, it is comparatively better than infinite, so it means we have to update this. And since whenever I'm taking this, I have to simply eliminate this part here, and when I'm further discussing that part. Okay, so since updating this part, and also post this in our queue there. So how to post this? So distance comma node, so it takes the distance as a 3, and what are its node? It is nothing but there's a 3 comma 1 there. Okay, similarly for the 2 we can update that part here, so we have to just cancel this part. And what are the distance it takes? It takes a distance 1, so we can update this part as a 1 comma 2 there. Okay, so this is the case. Okay, so now we can erase this part. Okay, so now what are its in front there? There is a 3 comma. Okay, so remove that part. So it means we are standing at the node 1, and in my what are distance taken to reach this 1, so it takes 3 there because it is 3 comma 1. Now what are its neighbor? Its neighbor has a 0 there, and another neighbor is as a 3 there. Okay, so we takes the 0 and 3 there. Now from the 1 to 0 it takes 3 distance, from the 1 to 3 it takes 4 distance there. Okay, so totally we can say it is the previous distance that it is from the to reach the 1. After it we have to add the edge weight to this, so it becomes the total is d is equal to 6. Okay, similarly we can say 3 plus 4, it is nothing but the d is equal to 7. Now we can compare from this method it takes a d is equal to 6, initially it takes 0, so which is better? 0 is better, and so we have to skip that part. Now you also understand why it gives me the 6. So it is nothing but the when we go to 0 to 1, so it takes me the 3. After it I can I have to come back here, so it takes me 3, so overall it takes me 6. But this is a worst, or this is a worthless thing, because we have to stand at here, so it takes me 0. So it is comparatively better because we have to give the minimum path there, so that's why we have to skip that part. Coming to this 3, initially it takes up infinite, now it becomes the 7, comparatively better, so simply update that part. Okay, so now update that part by the 7 there. Okay, we can verify also, so 3, 2 here and 4 here. Okay, and since we have to update this part, so after we have to update in our queue also, so 7 comma 3. Okay, so this is the thing here. Now just erase that part here after erasing this part here. Okay, now talking about this, so after it we have to use this 1 comma 2, means we are coming to the node 2, and it takes the distance to reach here as a distance as a 1, because it is 1. Now what are its neighbor? Its neighbor has it's a 0 there, and it is 3 there. It is nothing but the 3 there, and it is 0 there. Don't confuse this is nothing but the arrow representation. Okay, so 2 to 0 it takes a distance as a 1, from 2 to 3 it takes as a distance as 2. So totally it takes a distance 2, which is comparatively bad. Totally it takes as a 1 plus 2 means 3. Initially it takes a 3, 7, but now it takes become the you can see it takes as a 3 distance, initially it has a 7, means we have to find the one better, so we can update that part 3, and we have to put this in our 3 comma 3. Okay, now 3 comma 3 there. Okay, now we have to simply erase this part. Okay, now you see one thing here, since we see you see this part as clearly, we have the sum of the nodes arising in this case. There is a 7 comma 3, means in any of the path in any of the we don't have to remember what is the path there. In any of the case, we have to reach the 3 by using the total distance as a 7. Similarly, we have to reach the 3 with a total distance of 3. You can see either by this graph also, from 0 to 3, if we have to go through this path, 3 plus 4 gives the 7. Through this path it gives a 1 plus 2 3. Okay, now see, if I'm using this Q data structure, so I have to explore this 7,3 way, so it gives me the comparatively maximum path that I am using through this. Okay, because when I'm using this case, okay, if I'm here, let's say if I'm extending this part here, so it means I have to use this path. Okay, so it means it has to take the 7 distance to approaching to it. Now it takes 9 to this, and 7 plus 1 8 to this. Okay, so this is comparatively bad. And if I'm taking this 3,3, so it takes me 1 plus 2 3 there. Now it takes 3 plus 2 means 5 to reaching there, which is comparatively better. That is, initially it takes a 7 plus 2 9. Okay, so initially through this path it takes as a 9, but after it see, even I'm using the Q, it gives me the same result, but we have to skip, or we are able to skip some of the very bad cases, because we are already know that it gives me one of the extra cases that are optimized this path. Okay, so to avoid that part here, because it is nothing but this path, let's say if I'm calling this as a path 1 or upper path there, so it gives me the current, if I'm using this, so it gives me as a 7 plus 2 9. Similarly 7 plus 1, so it gives me the 8. Okay, now when I'm talking about this, mean the down path, so it reaches the distance 3, after it takes the 5, so 5 is comparatively better. Similarly 3 plus 1 4, so it is comparatively better. Okay, so to explore some of the further extra cases, because we know very well, this gives me this gives me the one of the extra cases, we don't have to find this, or these are not comparable, these are not actually matter in our answer, but they are taking some of the extra steps. So to avoid that steps, if how to we can avoid that part here. Now we can see one thing, what are the similar between these, since we are using the distance comma node. If I am coming to the same node there, and now what are the things matters to is as a distance, since if I'm see if there are the many of the edges given, many of the distances given, and if I'm saying there is a minimum distance, so why we do go for the larger distance cases, because I know this is gives me the useless cases that doesn't affect our answer. So to avoid that part, now what we can say, we should go for another data structure so that we can optimize that part. So this is nothing but our priority queue. So in that cases, what are it? It is first it is sorting or giving the minimum at top. So by this we can say this gives me the minimum at top, and similarly what we do in our queue, when we do extracting our elements from the front, so in this we have to extracting our elements from the top, and when we have to see the some of the cases from this. Now when we have to come to this 7,3, we know very well this gives me the comparatively bad result than this, because we already get the good result from this, so we have to generally skip that part. Okay, so that's why I have to use that PQ there. And see, this is the thing we have to use here. Now what is the thing, if I'm using the so this is the case remaining the same for all of the thing there. So this is nothing but our Dijkstra algorithm. And coming to that coding part, this is the same code here. We have to pass the total number of vertices, and this is our source node. Firstly I make our adjacency list, and if it is given, so we don't have to bother about it. Okay, now see, there is firstly I make the priority queue. So this is our priority queue there. This is nothing but the minim heap, and initialize our distance vector there with infinite. There's update our source there and push this in our queue. Now till the queue become empty, first I take, this is nothing but the int dis. Okay, int dis means what I'm using this. So if I'm extracting this, so it gives me the dis. Okay, it gives me the node. So don't confuse with the naming of the variable that I'm using here. This gives me the dis, this gives me the node. It means, and now after extracting this, we have to pop this part in our PQ. Means we have to this 0,0. So it means we have to reach to 0 using the distance as a 0. Okay, so this is the meaning. Now since we are talking about any of the particular node, now going to its neighbor, like how to do this. To going its neighbor, we have to use this edge weight. Okay, it's nothing but the our edge weight there, and it's nothing but the edge node there. Okay, what are its meaning? Since our adjacency list is like there, when let's say if I'm calling for this, so if I'm talking about the 0, so 0 has a particular node. So what are its neighbors? So there's a 1 and there's a 2. Okay, so in that cases I don't know like whether it is given there or not. Okay, so it is already seen there. Okay, so in that case you can see there is a 0, 2 and 6. So what are its meaning? It is nothing but the our u node, means our starting node. This is our final node, and this is the weight of our edge between the starting and the final, means 0 to 2. Okay, so this is the representation of our edge adjacency list. So how we extract this part here, like I'm using this code as my previous version of this, like GFG update is its question, but don't have to confuse about this. Actually I have to start this by using this. See there, from the 0 I have to what are its neighbor? It contains a 1. What are its edge weight? It contains 3. Okay, and okay, so exploring other neighbors, so there is another neighbor is a 2. What are its distance? It is nothing but the 1. Okay, so these are the 2 neighbors that are in corresponding or that are in neighboring of the 0. So this is the kind of the representation we are using for our adjacency list in the question. Don't confuse, again I am saying, don't confuse with the question pattern. This is a newer version, but I am using the older version code. So intuition doesn't matter there, like intuition doesn't change, so go for it. Okay, so like you have to make our adjacency list. I know like in my previous video I have to explain how to make the adjacency list. Okay, so now coming this, so it gives me the edge weight of IT of 1, means I am going for this. Let's say this is nothing but our IT, since I'm using our IT vector here, so it gives me IT. So IT of 0 means our adjacency node, mean our neighboring node, and it is nothing but our edge weight between them. Okay, now we see distance reaching or distance we are needing to reach our node, and plus our edge weight. If that total distance, if it is comparatively good, what we have to find in our previous past. Okay, so this is nothing but the meaning of this whole case. So if that is the condition arise there, that is true, we have to update and push this in our PQ in such a manner, distance first and node after. Okay, and similarly we can see if any of the node is not able to, like after we can check, we have to put this as -1. It means it is not reachable to that node. Okay, so like this is our simply Dijkstra, and like I can write directly what are its time complexities. It is nothing but the O of log E. Okay, so this is our Dijkstra code time complexity here. If you want like what's the intuition or what's the like derivation for this, so comment it. I have to explain in my further videos there. Okay, so like this is the I can say this. Let's wait a second. It is nothing but the okay, and if I'm talking, if any of the like further cases, or we can say any of the like further improvements we can do there. Okay, so we can do some kind of the further things here. Actually actually its time complexity is nothing but the E log V. Okay, that's why I'm confusing here. Okay, so this is the time complexity for our Dijkstra there. And like coming to this part, we can again improve this by using PQ. Like how to improve this, we can either take some kind of the another data structure that is nothing but our the set data structure. So SCT we can say, how is that set data structure? So we see if there are the some of the cases, like I don't do the trial for this case. Let's say there are the many of the path, and we are reaching to our path such that we are reaching the many of the cases in which two of the distances or two of the nodes are repeating there. Okay, so to avoid the similarly like that bad cases or that bad repetitions, we have to avoid that part. So we are using that set. It doesn't optimize like it doesn't means many major change in this, so you can like avoid that part here. Okay, so Now coming to this part. Okay, one of the main thing is that we can say our Dijkstra is not, we can say our Dijkstra is not work for negative, you can say edge weight, or you can say negative cycle. See, like keep reminding, this is different thing. Edge weight, any of the edge weight is negative, and the whole of the negative cycle, it is, these are the like competitive, these are sound similar, but these are totally different thing. If you are finding the confusion, you have to tell this in comments there. Okay, so see like how to do this. If I have to prove this why it is. So let's say if I'm using the graph, so this is my graph there, this is 0, 1 there. Okay, and let's say it takes me the edges of the 0, minus 2. Okay, now see, so let's say this is my distance vector. So this is nothing but the one node 0 and this node 1 there, and there's a one priority queue, and like I have to explain what's the necessity for the priority queue compared to queue in that cases. Okay, so first you have to update our, so this is nothing but the 0, 0. So we have to update this, and this is nothing but the initially it is a infinite there. Okay, now see, extract this part. Now coming to it, what it's meaning, we have to reach to our node 0, and what are its distance reach to there, it is 0. Now coming to the 1, what are its neighbor, there's only one neighbor. So let's say this neighbor 1, what are its distance, it is nothing but the minus 2. So 0, minus 2, totally it become minus 2, comparatively better than this minus infinity. Yeah, so we can update this part. Okay, and similarly we can update this in our priority queue there. Okay, so this is nothing but the minus 2, 1 there. Okay, now coming to this part, we are extending at the node 1, and what are the distance it takes to reach there. So it takes the distance as a minus 2. What are its neighbor there, so only one neighbor, that is the 0. So it takes the distance as a minus 2. Okay, now we see it takes the minus 2 there, minus 2 there, totally it takes the minus 4. When we check from where, so we see that 0 is comparatively better, like 0 is comparatively bad and minus 4 is comparatively good. Okay, so by this we can update our minus 4, but now we can see this is a wrong thing. Why? Because if I have to update my minus 4 with a 0. Okay, so like we see one thing here, let's say if I'm reaching the 0 with the distance, let's say in my previous I have to reach this by minus 4, and similarly I have to do the similar operation for the its neighbor, so it takes also minus 2. Okay, so that total distance takes minus 6, which is comparatively better, so we can update. Okay, so now you can see this is goes like in infinite loop. We can update this length, because comparatively it becomes the lesser length, like it become its negative, its magnitude is become the greater, but since it is of the negative, so that's why it becomes the less, because we can update it in each cases. So this is the fallacy. So now you can see like what's the like contradiction, why it fails for this. So we can simply see length is something that we have to expand, because let's say there is a distance, it takes a distance as a 2. So that means from the 0 to 1 it takes as a 2 distance, but now you can see there is a minus, so it's minus nothing something, like you don't have to spend on this, you have to give that, so that doesn't matter. So that's why our Dijkstra is not valid for these cases there. Okay, so now we can see one thing, like in my like description also I have to in my comments also I have to write the what's the time complexity for the like what's the simply the PQ and set data structure there. Okay, so actually I again said you there's not very much the difference between the two using these two data structures, so you can either escaping that part. Okay, because for the interview purpose it is comparatively it is we have to generally preferable our PQ. Depends on whether our edge weights are equal or not. Okay, if equal, so go for Q, if no, go for the PQ. So that's our question.